Okay, welcome to the Theory Frontier afternoon plenary. It's a great pleasure to be here to introduce our speakers today. Thanks, of course, to everyone for coming. Theory is essential to the enterprise of high-energy physics. Theory unifies the frontiers, and as a result, we've heard a lot about various aspects of theory in relation to all of the frontiers throughout the plenaries thus far in Seattle. But we also, for the first time in this snowmass process, have theory as a frontier. And one of the reasons for that was to provide a setting to articulate developments within the theory community, the things that will lay the foundations for experiments in decades to come. So in the pursuit of that goal, the theory frontier tried to involve the entire spectrum of high energy theory. So that included foundational or fundamental theory. It included computational theory, and it included phenomenology. And this was particularly notable because this is really the first time that fundamental theory has participated in the snowmass process at full strength. And it's been a real delight and pleasure to have fundamental theorists engaged in the snowmass process. So of course, we've already heard on Monday, beautiful lattice gauge theory colloquia articulating developments in computational theory. And today we're going to hear about visions for the future in both fundamental theory and phenomenology. So it's a great pleasure to begin that with Shamit Kachru, Professor Shamit Kachru from Stanford University. And Shamit will be articulating a vision for fundamental theory. All right, thanks very much, Shamit. Please take it away.
Thanks, Satoshi. Okay, can you hear me? Super. So we see on my first slide here, two pictures that will, I think, be consistent themes in much of my talk. One is a picture of a space of quantum field theories. In a sense, I'll try to make it a little more precise. One is a picture of a space of angels and devils. And there's a sense in which these two pictures are the same picture. And I'll talk about that also later in the talk. Okay, so I'm here to talk about fundamental theory. I put fundamental in quotes because I don't really exactly know what it means. But whatever it may mean, it's made tremendous progress in the last century. It's hard to summarize that very pithily on a slide, but I think these two figures do a reasonable job. On the left, we have a table of the particles that comprise our current zoo in the standard model. There's the somewhat recently discovered Higgs and the gauge bosons that mediate the fundamental attractions and the matter quarks and leptons around them. And on the right, we have some diagram that I think serves as a good benchmark for some of our knowledge of the concordance cosmology. On this axis, we have the density of matter, which includes the stuff we're made of and also the stuff whose presence we just infer through rotation curves and fancier techniques. And here we have the dark energy. And we see a whole set of different ideas about experimental bounds from type 1a supernovae, from CMB experiments, from cluster data, large scale structure, have given us increasingly precise knowledge of that cosmology. And together, these pictures, if you interpret them right, and you need probably a PhD to do that, really give us an explanation of a bewildering host of phenomena from 10 to the minus 19 centimeters up to about 10 to the 28 centimeters from subnuclear to Hubble volume. So our predecessors can be proud of this achievement. Now, the great thing about science, and the reason we all still, for the most part, have jobs, is that every answer raises more questions, right? And the questions that we get from those pictures are tantalizing. The standard model has some gauge group. It's a pretty garden variety Lie group. Where does it come from? There's some charged particle content with regularities, a little bit reminiscent of the regularities of the periodic table in chemistry. There's replication of structure. Does that mean something? Is the dark energy a cosmological constant, as measures of the equation of state currently suggest? Can we understand its value? The universe we see is pretty much flat. We're forced to learn Euclid's geometry in grade school and not something else. So does cosmic inflation explain the approximate flatness of the universe? If so, at what scale, with what properties? The Yukawa couplings in the standard model give us a lot of the rich structure of the matter particles. They have large hierarchies in their values. Can we understand those hierarchies? How and why is the Higgs boson so light? This hierarchy problem drove much of theory for decades in high energy theory. So these are questions that they're qualitative, but they're more or less directly motivated by data. But that same framework also suggests more qualitative questions. And I took as my job to explain some of the thinking about the more qualitative questions. So for instance, a particle missing from this little victory parade here is the graviton, which ought to be there if you quantize general relativity. And one embarrassment is if you take graviton vertices, the same way you take vertices of other kinds of particles in the standard model, when you start sewing them together in complicated ways to make a perturbation theory for quantum mechanical gravity, you get a set of divergences. We don't really know how to cure those divergences directly in field theory, though there's been really impressive work on amplitudes. The same theory that gives us our theory of low energy gravitons, general relativity, also has black hole solutions, which increasingly become an object of detailed experimental study and maybe even pictures. There are qualitative puzzles associated with the existence of black hole solutions. There's a horizon beyond which we cannot see and whose physics is associated with many puzzles, some of which I'll talk about. And then deep in the core, there's a singularity. And sort of by definition in physics, if you encounter a singularity, that's mathematics. Mathematics is a way of telling you that you don't know what you're talking about. So something has to give. Now, you might have thought that this is okay because after all, I just said there's a horizon. And if any time in gravity you encounter a region of ignorance, it's cloaked behind a horizon, maybe you could comfort yourself that at least it's hidden from you, even if you don't know what happens there. But unfortunately, cosmology suggests the existence of singularity theorems that tell us that everything we see came out of something that in our current approximations looks like a singularity. There's a cosmological singularity theorem. So how do we understand these kinds of singularities? Now, I can say, I think somewhat confidently, we don't have any examples of theories that we know to satisfactorily answer the full second set of questions, the qualitative ones, that I listed on that slide. I mean that even at the level of the kinds of toy models that theorists love. Okay, we don't know how to answer these questions. We don't know what a theory that answers these questions looks like. But all of these questions have helped motivate a really intense research program that has also dovetailed with experiment over the decades on two subjects, quantum field theory and string theory, that I'll talk about for most of my talk. Okay. So I'm going to try and report on where some of this large effort has been going and has gone. The community of researchers that have been engaged in this kind of work is really large. It's diverse in origin and interests and in opinions about theory. So I can't do better than to say the talk will be guided by my biases and my limited competence. And if somebody else gave this talk, you might hear a rather different slice of what's been going on. With that said, I'll proceed without apology. So I'll discuss first some of the lessons that we've learned in recent decades about quantum field theory, including some relatively new foci. Some lessons about mostly quantum gravity. And then finally, some important directions where I anticipate that there will be progress in the coming years. So let's start with some lessons in quantum field theory. When we take quantum field theory class, here I guess by we, I really just mean I suspect a lot of us had some more experience. We typically start with the expansion of a free field in terms of harmonic oscillator creation and annihilation operators A and A dagger that will create single quanta, right? So there's a scalar field phi and there's some form momentum k, and you expand it this way. And a free such field, maybe with a mass, would have a quadratic Lagrangian. I'm going to focus on Lorentz invariance because of my audience. So this is a Lorentz invariant field theory. And maybe there could be interaction terms like phi to the fourth, and if lambda is small, and we look at processes with small enough numbers of quanta for short enough times, we can treat interactions in perturbation theory, expand in the oscillators to our heart's content, and learn how to compute things. Okay, and this leads to a set of scattering processes whose amplitudes are computable in terms of Feynman diagrams. And it's decades of work, but it's also somehow conceptually a brief hop, skip, and jump from what I just told you about that simple field theory to the sets of rules that govern processes in the standard model. You use similar logic, you use similar expansions, you use a similar assumption of weak coupling, and you write down some Feynman vertices, and then you start iterating them and producing ever more complicated loop diagrams. And there are brilliant people who've worked on the properties of those amplitudes. I won't have time to talk about that, but there's been a lot of progress in understanding that. So perturbation theory has enjoyed tremendous success in this setting. An old-fashioned viewpoint, the one that I think I first heard, is that special theories, those that are quote unquote renormalizable, are especially preferred. They have magical physics in them. A more modern viewpoint, and I think it's in accord with what most of us learn now, is that of effective field theory. We keep the terms in the Lagrangian with all kinds of interactions, even those that are naively non-renormalizable. And if you don't remember what that means, I'll tell you. Meaning they're suppressed by appropriate powers of a high scale of physics that we haven't necessarily yet seen. So for instance, if we take our Lagrangian and we classify the operators that appear there by their scaling dimensions, if we imagine rescaling time and space in a relativistic theory, we would rescale them the same way, but say by a lambda, to go to long distances, we'd take lambda large. To make a Lagrangian that scales well, you then rescale the fields, and you can classify operators by how they scale with lambda. Okay, and what we learned is that at low energy or long distances, we can often ignore operators which scale to 0 in this long distance expansion. They're called irrelevant in the technical sense. They're certainly not irrelevant in other ways. While focusing on those that are relevant, meaning they grow more important, or marginal, meaning that we still leading order, their importance does not change with scale. So that leads to a picture of a space of field theories. You start somewhere with some Lagrangian that somebody told you to study, and the couplings flow. And then maybe a lot of the really irrelevant ones flow away, and you're drawn to some surface. And maybe there are magical points in that surface where the flow would stop entirely, where you have really a theory that no longer changes as you go to long distance, or conversely, if you went towards higher energy as you go to short distance. Okay, so this leads to this Wilsonian picture I started with of a space of field theories with flows connecting them. And this picture is just sort of about how QFTs flow as you go to long distance, or I could turn it around and try to study what happens as I go to shorter distance, though that would require more knowledge. So if you look at this picture and you think about what are the objects that I have the best hope of really understanding, somehow the fixed points of the flow are the natural quantum field theories to consider, because they're the starting or ending points of all of these flows. And if you understand the starting and ending point, maybe the properties of the intermediate theories are easier to understand too. The way a condensed matter physicist might say it is they contain the answers to all universal questions. In particular, they capture the universal properties of phase transitions in real statistical systems if they're second order. Okay, so a great deal of effort has gone towards understanding and classifying little tiny patches in this space of field theories in general, and most specifically in the set of conformal field theories, which I'll call space for a reason that becomes clear. Now, I don't know what kind of biases you grew up with. When I was a kid, I read that Lord Rutherford said that all science that isn't physics is stamp collecting. And if you make a list of objects, it feels a little bit like you're stamp collecting. And so to defend from that criticism, I have a quote from somebody in one of our sister sciences, Stephen Jay Gould, who is a biologist, and he talks about the importance of taxonomy in that sister science. And really what he's saying here is that classifications, if you're ignorant enough, don't just give you a list of things, but they teach you the organizing principles. And they may teach you which objects are so special that you should understand them more. And we'll see that later in the talk. So examples of such classifications, or at least in-depth studies in this space that have enjoyed some success, include those in two-dimensional CFTs, and something called the conformal bootstrap that's been undergoing a renaissance, and its cousin, the modular bootstrap, in theories with supersymmetry, and so on and so forth. So let me discuss a few lessons from these studies, and I promise the lessons will then carry over to the rest of the talk. So it's never popular to do this, but I'm going to first specialize to two space-time dimensions. We don't live there, but we can make such systems in the lab. Now, in two dimensions, you see, you could ask about the about the symmetries of the theories that arise at these fixed points of the renormalization group. I told you the symmetries included Poincare invariance by assumption. And because I was studying theories that no longer change when you rescale variables, when you go to longer and longer distance or lower energy, such theories also enjoy a symmetry under scaling. Under most conditions, that set of symmetries closes to a larger group of symmetries called the conformal group. Now, in 2 dimensions, there's a magical thing that happens in addition to scaling and Lorentz transformations. The conformal group closes to an infinite dimensional structure. This is very peculiar to low dimensions. But because that group is infinite dimensional, there's a lot of power. And so you can make progress here that you can't make in other dimensions. So as just an example, you could write this Lagrangian. You could have d phi squared. You could have phi to the 2n for some power n. There's a full, right, any integer you want. Well, in 4 dimensions, we would, or 3 dimensions too, we would work hard to study this theory, and we'd use perturbation theory, and this would normally be an irrelevant perturbation, and we'd have all kinds of technical issues. In 2 dimensions, it turns out these theories can be understood and solved exactly for all values of n. All correlation functions are determined by well-specified solutions to differential equations. And in fact, the theory is almost constructible algebraically. Like your colleagues in an F department might not look at you as being crazy if you explained this theory to them. Now, you might think, what a disappointment, we're supposed to be learning about our universe, and this guy is focusing on 2-dimensional theories. Let me tell you 2 reasons that this case is not an irrelevant peculiarity before moving on. The first is that critical phenomena in 2 dimensions, now 2 spatial, arise in labs. The second, and this is certainly relevant to my interest, is that this is the case relevant to what happens on the world sheet of what I'd call a fundamental string in string theory. I'll assume you've heard somehow, maybe colloquially, of string theory, right? And the fundamental objects there that you quantize are strings. So the world sheet of a string, the world line analog of a particle, is a 1 + 1 dimensional surface. Its collective excitations are then governed by a 1 + 1 or 2-dimensional field theory. And it's an old miracle that properties of that 2-dimensional field theory govern a lot of the basic physics of string theory. For instance, the equations for conformal invariance of that theory give you space-time equations of motion for the supergravity theories that come out of string theory. Now, it's not true that those theories can usually be solved. If you have string theory on some complicated curved space, you usually can't solve the model studying maps of the string world sheet into that complicated curved space. But early on, theorists did make the following speculation. It had 2 parts. One was that if you considered the space of all 2D quantum field theories, where those renormalization group fixed points were the endpoints of flows, then that space would be a suitable off-shell configuration space for string theory. And the CFTs would just magically cut out the on-shell configurations. And there was an even more optimistic conjecture that although most of these theories can't be solved, the exactly solvable points would be dense in the space of 2D CFTs. That is, close to any CFT you were interested in, a little perturbation would produce a solvable model. That was not obviously false when the conjecture was made. I'm afraid it's more or less obviously false today. But the reason I put it here is that it gives an illustration of how ideas about the full space of quantum or conformal field theories could potentially be important. Now, let me tell you something that's enjoyed much more recent enthusiasm, the conformal bootstrap. Our basic object will continue to be a conformal field theory. And given such a theory, you can give a list of its operators. One way to specify it would be you list all the operators and their properties. A special set that we'll call the primary operators are most important. What I mean by that is if you know these, you can determine the properties of all the rest. Now, a fundamental role in such theories is played by something called the operator product expansion. That may sound fancy, so let me explain it heuristically. Suppose you have 2 operators, O at x1 and O at x2, and they're over here. Here's O at x1 and here's O at x2. And you in the back are very far away, and you're like, that guy is pointing to the same point twice. So you basically say, why should I have to think of 2 different operators at x1 and x2, when in fact, they're basically at the same point, and I should be able to basically think of that insertion of 2 operators as a single operator insertion of some composite that you made out of their product. That basic idea can be turned into something mathematical. It becomes the operator product expansion that says, under the right circumstances, you can take products of local operators and re-expand them in terms of the basis of the full set of operators of your quantum theory. So very roughly, you can totally specify the theory by giving the following data: a list of the primary operators and the renormalization group dimension, how they scale. And then using this so-called OPE, The only correlators you know are 3-point correlation functions of those operators, which boils down to these coefficients Ci, J, K, that tells you how OK appears when you multiply OI and OJ. Now, here's a problem. You have a really mean professor, and this professor has assigned you to compute a 5-point function for your homework. Here are the 5 points. And you say, I'm going to use the OPE. But maybe the way you decide to do it is you group these 2 operators and take their product, and these 2 operators and take their product. But your friend with whom you're trying to compare homework answers first groups these 2 instead, and these 2, and then continues with the process. Well, life wouldn't be fair if the answer depended on how you chose to group those things, okay? And that means that not all sets of data that I told you are allowed. There are conditions called crossing conditions that basically just impose that I should be able to group these points however I want, take products, and then move on with the process and still get the same answer. And these equations can be summarized in this way, that if you have 4 operators inserted on the plane, you could either fuse 1 and 2 and 3 and 4, and that correlator would get a contribution precisely when they fuse to the same thing here, to the family of OI running in this channel, or you could first fuse 1 and 4 and 2 and 3. And if you sum over all possible things that they fuse to, those 2 formulas have to agree. That's some complicated infinite set of equations. So let's be simple. I promise I'll get to a concrete punchline in a second. Let's consider a 4-point function of 4 identical operators that are scalars under rotation. The simplest possible case. Okay, so they're all the same operator. Well, concretely, for a given OI appearing in this intermediate channel in the sum, we'll get a contribution to the 4-point function that's governed by a known formula that you can just compute. Okay, it's given by some invariant ratios of the points of insertion u and v. There's a function of those, g of u and v, divided by certain products of distance determined by scaling properties. And this g of u and v has the following property. At each of these vertices, there is the 3-point Cij, which here I've called f phi phi o. And for that contribution to be non-zero, that same f phi phi o, has to appear both on the left and on the right. And so you get a contribution to this correlator that's a sum of squares of f times some function g that's determined completely by the scaling dimension and spin of the intermediate channel operator, this g of delta and L. Now, I promise I'm getting to a simple point out of all of this, so don't worry if you got lost. The simple point is that we can write this equation 2 ways. One is we could write it for this side, and the other is we could write it for this side. And so what we end up with is 2 different ways of expressing the same correlator. Both involve f squared for the intermediate channel operator O. One has this g, one has this g. And what you see is that this is positive. This is some function, and this whole sum has to be 0 because the 2 ways of computing the correlator have to give the same answer. Now, you can't always take a bunch of functions, which you can think of as generalized vectors in some space, right? There's a vector space of functions. So this is a bunch of vectors. You're multiplying them by positive numbers, f squared, and that has to add up to 0. It is not in general possible to take a bunch of vectors, take a positive combination, and get 0. Okay, here's a simple picture where on the right-hand side, I challenge you to take a bunch of positive numbers, multiply these things, and get 0. So this allows you to test proposed CFT spectra numerically in very precise ways. The way to say this, maybe with more content, is that if you can find positive linear functionals that act on the combinations of functions that appear on this left-hand side, there, this is already positive. This is supposed to be 0. So you're going to end up with an inconsistency. And generalizing this very simple strategy, okay, it sounded complicated, but it's a very simple strategy, has led to really strong constraints of the following form. I propose that there's a simple conformal field theory with this set of operators and these properties. And somebody, maybe a member of the Simon's Bootstrap collaboration, runs it through this procedure and proves to me that that's impossible. Okay, so the really salient point here, this technique was discovered in the 70s. the really salient point here is that modern computing has grown so powerful that this kind of simple brute force approach is now tractable. You can take very large sets of these equations, bound their behavior, and start carving out which spaces of different conformal field theories are possibly allowed. Now, one goal of condensed matter physics has been to classify phases of matter. Classifying all possible critical theories would certainly be a meaningful step in that direction. And while neither the special power of 2 dimensions nor the bootstrap have allowed a complete solution of that problem, our knowledge of theory space has been considerably enlarged by both. Okay, here's a last example, and I'll transition. This last example is supersymmetry. Okay, you all probably know what supersymmetry is because it was very well studied as a candidate for beyond standard model physics. For each scalar, there should be a Fermi partner. For each vector, there should be a Gaugino partner, so forth. Now, there's still a lot of phase space to explore if this is going to be relevant to higher energy physics, and we have our fingers crossed, but it hasn't been discovered yet. But it's taught us a lot about theory space regardless. Okay, so let me talk about maybe the simplest supersymmetric theory, maybe the simplest interacting field theory in 4 dimensions, simplest from a theoretical viewpoint, which is the theory with the most supersymmetry possible. There are the most relations between bosons and fermions. It's the maximally supersymmetric Yang-Mills theory. So its field content is vectors in the adjoint of some group, gauge group, scalars in the same representation, there turn out to be 6 of them, and a bunch of fermions to make supersymmetry work. And the Lagrangian is what you guessed. There's a Yang-Mills coupling, multiplying f squared. There's a theta angle, like the theta angle in QCD, multiplying the density FF dual. And then there could be, scalar kinetic terms and so forth. Now, one of the remarkable things about this theory that leads to its simplicity is that actually for every value of g, and so g squared, which is positive here, and every value of theta, there's a conformal fixed point. There's a full half plane of conformal fixed points, one for each value of these couplings. In some sense, the flow is trivial in this theory. So one first lesson, not particularly interesting in general, is that manifolds of conformal field theories can exist. There are spaces of such theories, and they're interesting, though very non-generic. Right? For every g squared and theta, you get a fixed point. The more remarkable and interesting thing about this theory is that what I told you was slightly inaccurate in a really beautiful way. So if I let 1 over g squared run up this axis, and I let theta run this way, and conventionally we let theta go between minus pi and pi, okay, which are the left and right here, you might have thought the space of theories would be given by this full strip, where 1 over g squared is some positive number, and then theta goes between minus pi and pi. But it turns out this theory has a duality that acts on the coupling, in the simplest case by inversion. It relates the very strongly coupled theories that will be down here to weakly coupled things way up here. And so we get this more intricate space of conformal field theories. And the important point for the next part of my talk will be that by varying the couplings in the gauge group, for instance, SUN for any value of n, you find in this way many theories whose properties are very unconventional. They're very different from anything we've ever seen via perturbation theory from a free fixed point, and they get at a completely orthogonal set of questions that we're now going to discuss. Okay, so now I'm going to switch subjects. I've gone on and on about quantum field theory. I told you things that you may or may not care about, and now I'm going to switch to gravity. Okay, and this will seem like an abrupt change, but I promise a connection will emerge, and many of the ideas I told you before will come back. So it's been known for many years that there's a miraculous theoretical structure called string theory. The name is inherited from the fact that in the limits of its parameter space, it's described by perturbative strings, right, shown there. And some of the most exciting lessons of recent decades have come by trying to take the quest to find a non-perturbative version of this theory that goes beyond this picture more seriously. Now, somewhat surprisingly, a major step was taken by thinking carefully about the entropy of black holes. So let me explain. Now we come to another line of theoretical development that took many decades. Starting in the 1970s, relativists taught us some striking facts. There are black hole solutions of Einstein's equations. Real black holes, things like the one in the center of our galaxy, or even more massive ones that have the mass of many billions times the mass of the sun, you might think are relatively complicated objects. I mean, the Earth is bumpy and wiggly, so you might think black holes are bumpy and wiggly. But it turned out relativists could prove a theorem they called the no-hair theorem. Black holes have no hair, meaning that in an otherwise vacuum solution of relativity with a black hole at the center, only 3 numbers, the mass, the charge if it carries electric charge, and the rotation or angular momentum if it carries angular velocity, would completely characterize the solution. So these very massive and purportedly maybe extremely complicated objects are some of the simplest in nature in the sense that they're completely characterized by 3 numbers. A second fact they taught us is that if you look at the space of such solutions, right, instead of looking at one, you ask, what if I change this a little? What if I change that a little? What happens? How does it relate to other solutions? They obey a set of identities. That if you change the mass a little of one black hole, you have to change something else too. You could change its charge a little, and you could put a coefficient mu there. Or you could change its angular momentum a little, and we could put a coefficient omega there. Or you could change the area of its event horizon a little, and we put its surface gravity kappa there, so measure of the strength of gravity. And another fact that they taught us by considering complicated thought experiments where they scattered black holes off of one another and collided them was that try as they might in classical relativity, they couldn't make the horizon area shrink. The sum of horizon areas of any collection of black holes was monotonic. Now, one of the first classes you take as a physics major is thermodynamics and statistical mechanics, and these identities should ring a bell, right? So there's an analogy between these laws and the laws of thermodynamics. In this analogy, the area A of the event horizon is playing the role of an entropy. It turns out its coefficient above here is related to something called the Hawking temperature. And I'll just focus on one really striking fact here. The entropy, the analog of entropy in this formula, is an area. But if you think about a big black hole, its horizon is enclosing a volume's worth of degrees of freedom. It's a big sphere. Now, if you take a system that's more conventional, a bunch of spins in this room, molecules, whatever, well, you could change the orientation of the spin at each point independently. And so it's a basic fact that we'd expect the entropy of the spins to be extensive. It would scale with the volume. So there's something non-extensive about classical gravity here in this analogy with thermodynamics. Careful study of higher dimensional black holes in string theory has actually leveraged this basic observation that goes back to the 70s into a really remarkable tool, which goes under the name ADS-CFT duality. Okay, so let me explain that. The starting point for what most of us mean by gravity is Einstein's theory. So there's an action with a curvature in it. And there might be some vacuum energy, lambda. So that's the cosmological term. And I'm going to focus on a case that probably you thought little about, that with negative vacuum energy. So lambda is negative. Well, here's some facts. If lambda were 0, everyone's favorite solution of that theory is just flat space. But when lambda is negative, it turns out the analog of flat space, a maximally symmetric solution, is something called anti-de Sitter space. And it has the structure basically of a can. It's like a can where there's a center to the can, and there's a radial direction moving out from the center. As you move out in that radial direction, the other spatial coordinates and the time coordinate get rescaled. So there's sort of a Minkowski slice for each value of that radial coordinate in the can. And then the radial coordinate itself has this metric. This picture here is isomorphic to Escher's picture of angels and devils from my first slide. Now, there's a peculiar coincidence about anti-de Sitter space, which is that if you look at the symmetries of this metric, well, here you have Poincare symmetries for the slices of the appropriate dimension. You have this variable r, and it's clear that if you rescale r by some constant, nothing changes here. And rescaling r here could be compensated by rescaling these things. That means it has scaling and Poincare invariance, and in fact, it has the full conformal group in d space-time dimensions as a symmetry group. So that seems like a coincidence because we already encountered the conformal group once. That coincidence is explained by the following observations. First, in various examples, string theory has d-dimensional extended objects, branes, just like strings, except with d spatial dimensions, right? So here's a 2-brane, and their world volume, just like with strings, supports some effective quantum field theory governing its fluctuations, right? So there's some field theory on these branes that's d-dimensional. So let's consider, for specificity, the branes of spatial dimension 3, called 3 branes. their effective world volume theory would be 3 + 1 dimensional. It carries a stress energy, and they source a solution of the Einstein equations in 10-dimensional string theory. If the number of branes is large, that solution is weakly curved. We can reliably compute its properties near the core. And in fact, in a suitable limit, if we look very close to the core where the branes sit, the metric you get is precisely that of anti-de Sitter space. In fact, the anti-de Sitter 5 space, whose symmetries are the conformal group in 4 dimensions. There's also a sphere that goes along for the ride. That's the sphere that would surround the branes in the higher dimensional space. It would have been the horizon of the black hole we'd have gotten by considering a black hole solution based on those branes. Now, heuristically, in the cylinder picture where I had this radial direction, that radial direction in the cylinder picture takes us towards the branes at the center of ADS. And the field theory on those branes, in the real case of string theory where we can compute it, is the maximally supersymmetric Yang-Mills theory with gauge group SUN for n branes and with a coupling given by the string coupling. So that observation led to the conjecture that string theory in a suitable background is in fact exactly the same as supersymmetric Yang-Mills theory. Okay, one is a theory of gravity in 10 dimensions. One is a 3 + 1 dimensional simple supersymmetric conformal field theory. And the argument is that they actually have exactly the same properties as long as you're smart enough to decode the dictionary. Okay, the super Yang-Mills is a theory governing the horizon entropy in analogy to our earlier discussion of black holes. The curvature radius of the ADS is large, or the curvature is small if n is large and if the coupling is kept fixed. And so we get a regime that we can control in thinking about this theory if we take n to infinity and keep this coupling fixed and large. These field theories are precisely some of the weird beasts I talked about in the third section of my discussion of quantum field theory. The weird things that show up on that plane of fixed points of n = 4 super Yang-Mills. Okay. Their peculiar properties, and I realize I'll need to wind up pretty soon, are the following. They have a large number of degrees of freedom. The n has to be very large. They have a sparse spectrum of operators at low conformal dimension. It's hard to emphasize how surprising that is for a theory at large n, but it's true. And they have large, and I mean very large, anomalous dimensions for almost all of the operators that are not protected kinematically. This list of properties is never true of any conformal field theory that we access by doing perturbation theory around free field theory. But by learning about these objects, what we've done is stumble across a new kind of free definition of a quantum field theory, but it's a free definition in terms of higher dimensional supergravity. Okay, so there's a whole other corner of the world that we didn't learn about in our field theory class. Now, this provides an amazing example of emergence, right? A full gravity theory is coming out of some field theory that you were playing with as a simple example. And it also provides us with a candidate non-perturbative definition of string theory, but with very particular asymptotics. So in my last 4 minutes, I hope, I'm going to discuss 2 significant foci of recent work that I think will carry some activity in the study of quantum gravity much further. One is obtaining a deeper understanding of how this kind of duality works at all. And the other is pushing to expand it to what I'd call more interesting spacetimes. Okay, so I'll do this cartoonishly. One interesting direction is just nuts and bolts of what I told you. So a correspondence between a d-dimensional theory without gravity, a field theory, and a d + 1 dimensional theory with gravity, a 4D field theory with ADS5, begs certain questions. How are the degrees of freedom of the gravity theory encoded in the quantum field theory? There has to be some very interesting encoding. Can we engineer quantum field theories to emerge a designer gravity theory of our desire? Could we emerge the standard model coupled to gravity from a suitable choice? Let me just describe 2 qualitative insights in this direction. Okay, and this begins to connect us to other fields. The first insight is that quantum entanglement is a natural object in the bulk. So we all learn about quantum entanglement after the beautiful thought experiment of Einstein, Podolsky, and Rosen and the discovery of the Bell inequalities. Here's the poster child example of quantum entanglement. You have a system, a bipartite system of 2 spins. Here are 2 natural states. You could take the state spin up plus down of one of the spins and spin up plus down of the other and take their tensor product. Or you could take the state spin up times spin up of the 2 systems and spin down times spin down. Now, with little education about quantum theory, you might not particularly think this is a significant distinction. But a little bit of thought shows that even qualitatively, they have really different properties. Because in the top system, if you measure the first subsystem and find spin up, your ignorance qualitatively about the second subsystem remains significant. Whereas in this one, once you measure spin up for the first spin, you have a lot of knowledge about what the second spin is doing. Okay. A way to quantify that for more complicated systems is something called the entanglement entropy, where you take a density matrix describing what you've done, you take a partial trace, and that gives you a measure of the entanglement. Now you can ask the same question about quantum states in quantum field theory. How are they entangled? And it turns out that in exactly this holographic setting that I've been describing, there's an amazing and simple geometrical construction that answers the question. So if you take a quantum field theory on this plane, or in 3 dimensions, which I couldn't draw in the example I discussed. So there's a region A, it has some boundary. We could ask, in some quantum state, described both on the boundary and in its dual in the bulk, what is the entanglement between A and its complement? What is the entanglement entropy? There's an amazing formula. The entanglement entropy between A and its complement is actually measured in appropriate units by the area of a minimal surface that extends from the boundary of the ADS geometry into the bulk that you can compute using classical general relativity. So quantum entanglement is a classical property of the gravity dual and a simple, beautiful classical property. This has served as a launching point for many investigations into the following question. Which region in a boundary field theory, like A, encodes which part of the bulk geometry? Okay, and a simple qualitative idea that comes out of this is the following. Imagine breaking the boundary into 3 regions, A, B, and C. Here's some point in the bulk. Well, we can get a minimal surface with boundary B plus C, boundary of B plus C, that includes this point, or boundary given by the boundary of A plus B, or the boundary of C plus A, right, like this. What that means is the physics of the point in the bulk could be encoded by an operator in the field theory, supported on any of these regions, which are distinct regions. And this indicates that there's a duplication of information in how the bulk physics is encoded in the boundary. And it's thought to be an indication that quantum error correcting codes play a key role in whatever dictionary goes between bulk and boundary. I'm not a quantum code person, but I think the words that would be used by such people, forgive me, I'm not one of them, is that the bulk corresponds to the logical qubits of some system and the boundary to the physical qubits. Okay, and there's a redundant encoding of the logical qubits in the physical qubits. Okay, and lastly, I know Nate is about to grab me and strangle me. I have one last thing to cover. More interesting spacetimes. ADS space is a great playground for theorists. The boundary locks down fluctuations. There are boundary conditions, nothing wild can happen. ADS space plays well with supersymmetry. Theorists play well with supersymmetry. It's a really happy marriage. But for better or worse, we don't live in ADS space. And key features of both Minkowski and de Sitter space are very different from ADS. Here's some relatively recent DES plot of the equation of state parameter measuring today's accelerated expansion against omega. And these plots and others from the early universe data coming from CMB suggest that the case of accelerated expansion in general and de Sitter space in particular seems particularly urgent. Okay. There's been a lot of work obtaining semi-classical de Sitter solutions instead of anti-de Sitter from string theory. There is absolutely nothing as simple as the supersymmetric ADS solutions. Approximations and effective field theory play an important role, and so it's hard to give a decisive story. But one lesson from these constructions is that de Sitter space will almost surely be metastable anytime it arises in string theory. It would arise as some approximate vacuum that could tunnel to 0 string coupling or very large volume of the extra dimensions to an asymptotically FRW or flat space. And so one line of research is seeks to embed de Sitter holography in an asymptotic boundary of a space-time decay product of such a decay. Don't worry, two slides. Okay, a more recent approach, particularly effective in 2+1 dimensional gravitational toy models, uses something now going back to 2-dimensional field theory, to 2-dimensional fixed points. And in particular, the remarkable properties of a new tractable deformation of quantum field theory studied intensely in recent years. Okay, so coming out of work of the Russian School of Theoretical Physics, there's a very peculiar deformation of two-dimensional systems by a product of stress tensors called the TT bar deformation. It's naively an irrelevant deformation. It has dimension too big to add and flow to low energy and keep it. It seems to grow more important as you go to higher energies. And there's a differential equation that tells you how the action of the theory changes as you evolve up in this coupling lambda, multiplying the stress tensor of the theories. The special properties of stress tensors in 2D CFT make this deformation tractable. And the recent work that I think starts to get at a new approach to de Sitter holography starts with 2D CFT duals to ADS3 gravity, deforms both sides by this kind of special flow and some other things. It argues that a patch of the geometry that contains the black hole horizon in ADS space morphs to a patch of de Sitter space in 3 dimensions containing a cosmological horizon, with the 2 horizons being identified. Then things like the Gibbons-Hawking entropy of de Sitter space emerge precisely from a state count in this system, a state count possible because of the special properties of 2-dimensional quantum field theory. So I believe that this general direction is going to be well motivated going forward of trying to understand holography for more realistic systems. Here's my last slide. I think I just want to close by saying I think our current state of knowledge of theory space, just in the simple playground of quantum field theory and gravity, is somewhat like this picture of Earth given by the Hunt-Lennox globe from 1510. So what is this globe? If you can read this, there's a language that I don't know here, probably Latin, that says "here be dragons." This globe is the basis for the legends that medieval maps used to say "here be dragons" in regions where they didn't know what was there. And I think our knowledge of theory space is sort of like this globe. I think continued exploration will reveal qualitatively new regions, as we saw here with field theories that emerge gravity. And because there are big questions about nature that we can't answer today, I think it will be worthwhile to understand the space of theories better on its own terms. Thanks for your attention, and sorry for the time.
Thanks very much, Shamit. We have time for a few quick questions, both from the audience and from those participating on Zoom. Well, I can abuse my privileges to ask you a question. It's actually 2 questions. So oh, there is, great, even better.
No, so this is just to clarify what you mean by recently. So some of the stuff, ADS CFT is 25 years old. So what things that emerged, just to be arbitrary, since last snowmass, for example?
Tell me. Yeah, you can see I was short on time because I had to be coherent, but the connections of the way the bulk boundary map works with quantum information ideas, in particular, this thing I talked about with error correcting codes, and then a much more extensive dynamical body of work that relates properties of solutions of near black hole horizons to properties of spread and flow of entanglement in thermal states in quantum field theory, has been a really significant focus of activity. So the very tip of that is what I showed you with the quantum error correcting codes. But I think maybe the word entanglement and the general notion of how entanglement maps across duality, how entanglement manifests in space-time, how does entanglement flow in a quantum theory if you perturb an entangled state? These have been directions that have both seen great activity and also incredibly fruitful overlap between high energy theory, quantum information, and condensed matter theory. So I'm not exaggerating there. You can count the number of condensed matter papers that are studying sort of flow of entanglement. It's immense. Does that answer your question?
Yeah, thank you.
Time for one more question. All right, maybe I'll ask you my double-sided question, Shamit. So as an emissary from fundamental theory to the snowmass process, is there one thing that you would like us to know, us broadly, in experiment and more phenomenological theory, to inform something that you think that we should know from fundamental theory? And then on the flip side, is there something that you want to know, particularly from experiment, that would help you?
I mean, now I'm just going to give you my own biases. My bias is that we have something incredibly important and interesting to learn from what happened in the very early universe, and colliders may also shed light on it, having to do with the physics behind the initial accelerated expansion. And that may teach us lessons both about the origin of the universe. I mean, that doesn't mean anything. We always just push it back one step further. But we now know the hot Big Bang is probably not the origin of anything except reheating of quarks and leptons. So there's a stage before that. We'd like to learn about that. And a lot of present data is starting to teach us about that. And a lot of that is discussed at this meeting. And colliders provide a complementary viewpoint on that. If there were a question that you might answer that I would really like to know the answer to, and I'm going to say this in the sense of people who wake up and say the Riemann hypothesis, something I personally would be really happy to know is somewhere beneath the Planck scale is there supersymmetry. I find that an important aesthetic question, and it's probably also important physically, but I'd really like to know.
Thanks very much. All right, let's thank Shamit again for his excellent talk. All right, so that was a vision for fundamental theory. Now we turn to a vision for, or rather as Jesse's put it, the frontiers of phenomenological theory. And so from this, we have the tremendous pleasure of hearing from Professor Jesse Thaler from MIT. Jesse, please take it away.
Great, can you hear me? And also, could you move the caption box up into this labeled corner?
Jesse.
Is the answer no? Oh, it's trying to get there. Okay. So this has been a really fun week for me. I left Boston with a blank slide deck, and I decided to be inspired by the things that are hearing this week. And so what you're going to get is a smorgasbord of ideas coming from the interface of theory and experiment, enabled by the unofficial mascot of the theory frontier, the wonderful coffee shops around here in Seattle. So I was thinking about what theory actually is, and in talking to some of my colleagues, we decided that theory is the rigorous study of what is possible. And you heard this already in Shamit's talk, talking about what is possible, ADS-CFT, TD bar deformations, things like that. But as a phenomenologist, what I care about is what is possible in our universe with experiment, the ultimate arbiter of what actually is. And when you think about a phenomenologist, I want you to think about Ann Nelson, pioneer of the possible. We had a memorial workshop for her right before Snowmass. She was someone who was fiercely independent, incredibly creative, had a deep respect for experiment, but had her own theoretical compass, and someone who cared a lot about building a vibrant physics community. I want you to think about her and think about all the ideas that she explored, things like supersymmetry, model building, baryogenesis. But also when you think about someone working in phenomenological theory, of course, we have the standard model itself and summiting the known phenomena, things that we think we understand. We think we understand the standard model of particle physics and cosmology, and yet working out its detailed implications is a real grand challenge in our field. So why pursue the possible? You're trying to fix the caption box? I'll just keep talking. So for me, I'm inspired just by my own curiosity about how to properly run, my own human curiosity about the universe, that I got into theoretical physics to answer the question why. But from a more practical perspective and trying to answer the questions of the hows of the universe, rigorous speculation has a pretty good track record in high energy physics. And I would have been saying that more confidently if we didn't have our public lecture this week, which is an example of, I think, of a case for physicists for caught flat-footed. But in terms of the fundamental ingredients of the standard model, in many cases, the theoretical understanding of that preceded its experimental observation, most notably in the case of the Higgs boson. So this is, why doing it, but in the context of, our planning as a field, you can ask, why should we invest in this? After all, high energy physics is ultimately an experimental science. But talking with my colleagues in the theory frontier, the things that we want to emphasize to you is that theory advances our understanding of nature in regimes that experiments cannot yet reach. And you heard this in Shamit's talk, explorations of what could be, whether it's in our universe or some hypothetical one. That theory establishes the conceptual and calculational foundations for future experiments. Some of the things that Shamit was talking about in terms of scattering amplitudes, for example, once that technology matures, it's going to have a big impact on the way that we actually analyze data, we think, from colliders and cosmology. In fact, it's already having an impact. Here, I'm going to be emphasizing the fact that theory is essential for motivating new experiments, analyzing, interpreting experimental data, responding to experimental surprises. But also, I want to communicate at the same time that theoretical research is a vibrant scientific endeavor in its own right. And our field has our own motivations and methods, some of which you're going to see on display in this talk. So, as I said, I got on the plane with a blank slide deck, which is a little bit daunting. And I was trying to figure out what you would want to hear about. And I was talking to folks at this workshop for Ann Nelson, and I realized that I had already written half of my talk back in 2019. I had my own personal snowmass. Joanne Hewitt invited me to give a presentation to the High Energy Physics Advisory Panel in 2019 with the title of The High Energy Physics Landscape in 2019. And I decided that it would be fun, I think you might be interested, to see what was I thinking about prior to the snowmass process. And so I'm taking content that's 3 years out of date, only lightly edited, so you can see my thinking, and then we can compare my worldview in 2019 to where we are right now in 2022. So here's what I said to the High Energy Physics Advisory Panel about the state of our field 3 years ago. So the universe is a big place, spanning 60 orders of magnitude of fascinating dynamics, from the size of the universe itself to the scale where we think that space and time breaks down at the quantum gravity scale. 60 orders of magnitude of phenomena, of which the standard model, the standard model actually explains a fairly large range of phenomena, anchored by two of the deepest mysteries that we have: the origin of dark matter, or the nature of dark matter rather, which dominates gravity on galactic scales, and then electroweak symmetry breaking, the origin of mass, which is active at the TeV scale. And beyond these are even more questions, the questions about acceleration of our universe, both in the past and now, questions about hierarchies between the electroweak scale and the quantum gravity scale, neutrino masses, where we don't really know what scale that's operating at, strong CP problem, the flavor structure, matter-antimatter asymmetry. These are the puzzles that we're all trying to understand the answers to, with our own different ways of approaching them. As a theoretical physicist, I actually like to reframe this. I mean, this is, as I said, the kind of colloquium edition of how I talk about the HEP landscape. But if I want to talk about the quantum field theory version of this, the quantum field theory version of this story is, this is the standard model in a box where you don't even need to specify a Lagrangian. All you need to say is, please write down the leading interactions consistent with these symmetries, the famous SU3 cross SU2 cross U1 gauge symmetry of the standard model, 3 generations of fermions coupled to a Higgs. And that by itself specifies the standard model. You don't even need to write the Lagrangian on your mug, because we have the principles behind this box of quantum mechanics, Lorentz invariance, spin statistics, and so on, that tell us how to translate these words into mathematical equations. We also have principles that we don't know whether they operate in nature, principles like the principle of naturalness, whether we think that radiative correction should be under quantum control. And then coupled to these principles are the paradigms that we think are active in our universe, paradigms like the way that chiral masses are generated, or asymptotic freedom of the strong force. And then a huge number of question marks here, where we don't understand what paradigm is realized in nature. For example, we don't know whether neutrino masses are Majorana versus Dirac. We don't know exactly the mechanism that's generating those masses. And so kind of looking at this list of questions that I had, how does this map onto what we're doing in our field as a whole? And okay, this is the science drivers you see many times, P5. And I concluded, at least in 2019, that they were well aligned with the core questions in fundamental physics, and that this has been an effective roadmap, which we've discussed. But one of the things that I felt was absent graphically from this, graphically, there's something in the middle that we can put in there. Okay? We can add that what we do in our field is develop transformative concepts and technologies to enable future discoveries. And so here's this yellow pentagon that represents, in addition to reaping the physics rewards of key investments, we're continually planting the seeds for future explorations, of which theory is an example of planting those seeds and see where they grow and where they develop. And I called this P5 prime. Anyone who knows B physics, so apologies to the BK plus P minus anomaly. Okay, P5 prime, and this is not a difference than P5. This is a statement which we've heard, I think, in Snowmass about what's at the core of some of the research that we're doing. So let me just take this yellow pentagon and kind of move it around, and it will make little appearances. Again, these are slides from 2019, but the one thing that I do is I took this yellow pentagon and tried to show you where it appears, at least from the theory perspective. So from 2014 to 2019, we saw the solidification of the standard model, incredible agreement between theory and experiment in the context, in this case, of collider physics, a triumph of both areas. And this transformative technology of theory, the precision calculations that we built to actually do this detailed comparison, lays the foundations for future explorations for physics beyond the standard model. In the same type of time period, we saw a diversification of BSM searches. Sometimes we show these bar charts to represent the search coverage that we have in colliders. Each of those bar charts, in some cases, often has additional sub pieces in it. Here's an example of a CMS analysis where this green curve was enabled by theoretical work that came from the jet substructure community, trying to figure out different ways of slicing and dicing jets in order to look for boosted objects. And in the case of this boosted object, a hypothetical Z prime decaying to Q cube R, the last time we discovered in the hadronic final state something going to Q cube R was at SPS with the W and Z bosons. And now we're setting the strongest bound since that using jet substructure techniques developed in 2014. And a wide range of innovative analyses with broad coverage, again, coming from these transformative concepts and technologies. We've established new paradigms. Extended symmetries are one of those things. Shamit mentioned supersymmetry, a way of addressing some of the shortcomings of the standard model by adding additional space-time symmetries or other types of symmetries. That's one type of transformative concept. More recently, the idea of hidden sectors, which is arguably the generic structure that comes out of string theoretic scenarios, where you have a hidden sector that might contain dark matter, talking to the standard model through some type of weak portal. And these new paradigms motivate new search strategies, new ways of probing the dark sector. And then the last example of something which has continued to be relevant today is the continued effectiveness of effective field theories. And if I take the 5 science drivers and I ask, does effective field theory have something to say about it? And each one of those it does. Electric symmetry breaking can be described in EFTs. Understanding neutrino masses and mixings can be understood in terms of a dimension 5 Weinberg operator. We can build testable dark matter paradigms. We can accommodate but not explain current acceleration of the universe. We can even understand why further deviations are suppressed in terms of power counting in effective field theories. And even if you want to understand quantum gravity, effective field theories have something to say. And if you're willing to live in the weak field limit and don't get around anything that's strong gravity, you can actually quantum mechanically couple standard model to gravity with one free parameter at the Planck scale. And this incredible technology of effective field theories enables systematic probes for cracks in the standard model. And this has had an impact and continues to have an impact today. So this is what I said back in 2019. And 21 slides later of evangelizing about all the amazing things that are going on in the field, I conclude in the following way. Looking forward to now. It's kind of strange to be talking to myself in the past. Anyway, so the physics priorities of our field are largely the same, but the toolbox and targets have expanded. And another thing that I thought that was missing from this logo here was something that came up in the community engagement forum earlier this week, that another thing that our field needs to be doing is cultivating a vibrant, inclusive, and supportive scientific community. And that the success of the endeavors that we do in high energy physics depends on 4-pi coverage and identifying and cultivating talent at all career stages. So again, this is what I was making in 2019. And now you can ask, 1,150 days later, is this still resonate with all of us now? And at least through the conversations that I've been part of and listening to people here, it seems like, yes, that's indeed here. We're finally here in Seattle. And I think I've heard many times that for the science, it requires an investment in the technologies, the concepts, and in the community. And this is reflected in the way that we're organized in terms of frontiers this time here. Right. So this was the easy part of my talk, because these slides are already written. This was a snowmass of 1. I got to just think about what was in my head. I didn't have to have conversations with my colleagues saying, oh, you should show this slide, and you should show this slide, you should show this slide. And so now somehow, now that we're here, I somehow have to tell you about the frontiers of phenomenology and communicating the fruitful and essential dialogue between theory and experiment. And somehow I'm supposed to do that for a theory frontier that spans a huge number of topics, of which Samit has covered a few of them. But if I think about all these, these map not exactly one-to-one, but kind of one-to-one to each of the frontiers. I'm basically talking about the whole high energy physics community, and I'm looking at the clock, and there's not so much time. And so what I've done is I've selected kind of smorgasbord style, some kind of idiosyncratic examples. Idiosyncratic just in the way that theoretical research is idiosyncratic. And I want to thank everyone who gave feedback. I want to apologize for everyone whose feedback ended up in my backup slides. And these ideas belong to many people. So I'm showing specific plots, but really it's the work of the theory community as a whole that's driving some of the things I'm talking about here. So here are, I can't remember whether it's 5 or 6, some number of examples of things that are going on, which is having a real direct impact and dialogue with the experimental community. So the first thing, cueing the montage, is the Higgs boson going from discovery to precision. And this is a plot showing the evolution to the next and next and next to leading order calculation, the Higgs boson cross-section. And the time here is crucial because we discovered the Higgs boson in 2012. Had we discovered the Higgs boson before the NN LO calculation had been there, we would have interpreted the measured Higgs boson cross-section as being a deviation from the standard model because of the large corrections showing up at this order. So multi-loop, multi-leg, multi-log calculations are reaching unprecedented accuracy, and they're essential for interpreting measurements that we're making in colliders. Some of these calculations we can embed into event generators. And I really like this logo that came out of one of the event generator white papers showing the connections between proton-proton collisions, parton showering, even for forward physics facilities, and also neutrino scattering on nuclei. And one of the things that I knew about but didn't really have in my bones is how challenging it's going to be to take theoretical calculations or theoretical insights that are coming out of some of the calculations I showed you before, but also non-perturbative modeling, and enabling the US long baseline program to get ready for neutrino argon scattering. And here's a plot that's showing electron argon scattering, where the data in black versus the predictions out of a generator don't match in a way that we're going to have to synthesize lessons from high energy parton showers with non-perturbative modeling and lattice inputs if we're going to be able to have event generation that can tackle this particularly challenging scattering scenario. In terms of other puzzles in non-perturbative QCD, there's been a lot of talk about muon G-2, and we had a great discussion of this in the lattice session. And it's fascinating that different ways of extracting the muon anomalous magnetic moment seem to give you different answers. I view this not so much as a search for new physics, by the way. I view this as an over-constraining of the standard model. If you use the R ratio or if you use a lattice extraction, you should get the same answer. And so the fact that we're seeing some kind of mismatch here, it could be evidence for new physics, but it's certainly evidence that we need to understand QCD better in the non-perturbative regime. And there's a similar kind of tension that maybe I'm the only one who cares about the extraction of the strong coupling constant from lattice and other areas, and then the extraction coming out of event shapes. This is a situation where it's one QCD. It should be able to describe high energy phenomena, low energy phenomena. These event shapes are cases where you're actually spanning over a range of energy scales. And I'm really excited to see precision, not just precision in terms of an individual value, but precision meaning that we have multiple different ways of over-constraining the standard model to make sure we understand its structure. Another puzzle that's come up is violations of lepton universality in B decays, where penguin diagrams involving muons seems to somehow be smaller than penguin diagrams involving electrons. And this is a case from the interpretation perspective where effective field theories have shown their continued effectiveness. And this way of visualizing what's going on is showing that the LHCb results differs from the standard model, and the way it differs could be mapped out by different types of operators that you can induce. And then those operators that you can induce tell you what types of new physics models you should build. Those types of new physics models you should build inform what types of collider searches you should do, what type of collider searches you do, and all the results tell you then how to go back. And so this is a particular puzzle that, whether or not it persists, launched a mini industry of theory work that broke down old prejudices and inspired new analyses. And in my case, I had to accept grudgingly that there could be new physics that showed up in a second generation. A lot of my work when I was a PhD student had to do with new physics showing up in the third generation involving the top physics. But the idea that something could be special about the muon, that was very puzzling to me, continued to be puzzling to me, but again, made me change my perspective with the synergy between experiment and theory. And then planning for the far future, with apologies to the t-shirt folks, that if you're going to venture on a multi-generational voyage into the unknown, then you have to have some idea about where you're going. And to figure out where you might be going, wouldn't it be nice to have a theory community that can tell you, hey, for these well-motivated dark matter scenarios, what do we think about its cosmological history? in terms of interaction strengths. Then how do you map that onto the luminosity and then the energy of a collider that you're going to build? And so you really need these lighthouses on the shore that theory is erecting to give you some guidance when you're trying to plan for these far future endeavors, even though ultimately, I think at the end of the day, it's going to be the things that we haven't anticipated that are going to be most exciting for any type of project that we build. And so, these 5 examples, again, more in backup, are showing you the continuous importance of studying the possible, that theory is essential for motivating new experiments, for analyzing and interpreting experimental data, responding to experimental surprises. And at the same time, the way that we're approaching theoretical research is a vibrant scientific endeavor in its own right. And part of the reason why you're going to see that it's a vibrant scientific endeavor is that there's going to be someone who during Q&A is going to ask me, Jesse, why didn't you talk about this? And I will say, you're absolutely right. That's also really exciting. And actually, I encourage you to ask that question, highlight some of the things that I didn't highlight here. Now, there's more to my talk, a whole nother part 3, which is what I would view as this expansion of theory and trying to communicate the way that phenomenology is evolving since the last snowmass. And this also has experimental relevance, but for me, this is more about thinking about how the community of theorists has changed and the type of tools are changed. And I just want to call out Flip Tenedo, who made this logo for the Theory Frontier. I have no idea, Flip, whether you also have a love of pentagons, but thank you for incorporating that into your logo. So here are yet another montage of ways that theory is evolving and changing. And one of the things that was highlighted earlier this week was the fact that modern machine learning is really affecting our field. It's showing up obviously in experimental analyses, but it's not just more of the same. It's not just more statistical analysis. For me, it's galvanizing a conceptual shift in our data-rich field. These type of techniques are being used, for example, for anomaly detection. So this was an example from the LHC Olympics, a kind of stress testing of anomaly tools, where you actually had a number of techniques that were able in an unsupervised way to identify new physics. Then you had this human neural network, which is a team that I was involved in. And you should ask me in Q&A how we got it so wrong, why we were outsmarted by the machine. But it's not just new physics searches. It's not just things that are speculative. This is also giving us new insights into phenomena like those in QCD. And so empowered by the public release of open data from the CMS experiment, empowered by funding from the National Science Foundation for the institute that I direct, the Institute for Artificial Intelligence and Fundamental Interactions, and a suite of different machine learning techniques put together, we're actually understanding new things about QCD. I show you this plot. This plot does not look like it uses machine learning. This is very heavily machine learned using things like topic modeling, optimal transport, equivariant neural networks, and things like that. This is something that a data scientist would call a intrinsic dimensionality. A quantum field theorist would call this an anomalous dimension. And bringing together people with quantum field theory knowledge and data science knowledge is giving rise to this kind of new category of data physicist, a different type of theorist, who also thinks about data, which also interfaces with computation, which also interfaces with experiment, really kind of new category of person entering our field. Revisiting fine-tuning, I had to use this picture of the sculpture that's out there on the quad here. And we can ask the question, is naturalness a reliable guide into the unknown? We had a beautiful talk from Hitoshi earlier this week, talking about why we think there might be or must be new particles to regulate quantum corrections of the Higgs. And he contrasted that with the case of the electron, where there were new particles that regulated the electron's properties, namely the positron. But this idea is being challenged in interesting ways because some of the things that we've learned from quantum gravity is that there are no global symmetries in quantum gravity. And the logic that we use to say why we're not concerned about the electron is global symmetries. And that actually challenges what's known as technical naturalness. And this is something that I learned from reading one of the theory white papers. I encourage you to read this. This is in a coda of one of the white papers. Does this have implications for flavor physics? Do I now have to worry not just about the Higgs boson, not just about the cosmological constant, not just about neutrino masses? Do I have to worry about the entire flavor structure and the small numbers and worry about their stability under quantum corrections in a quantum gravity theory? Maybe, and maybe that's going to be exciting and generate different types of paradigms or worldviews. Effective field theory, if there's one hero in both my talk and Nishamat's talk, it's effective field theories. This toolbox has been incredible. And building on the successes of heavy quark effective theory, non-relativistic QCD, soft collinear effective theory, standard model effective theory, Higgs effective theory, we're also seeing it going into new regimes, like understanding inspiraling binaries in the context of gravitational waves, as well as the effective field theory of large-scale structure. And the reason why you're seeing effective field theory all over the place is that hierarchies of scales are ubiquitous in science, and that's the reason why effective field theories have broad impact beyond just traditional HEP applications. And when I was learning about EFT of large-scale structure in the white paper, I came across this plot, which I found remarkable as a reminder that data analysis spans theory and experiment. This is an effective field theory analysis of BOSS data, where you're comparing, in one case, a single author theory paper with one data set to a 181 author experimental paper from a different data set, representing two different ways that one can engage in data analysis. This is especially true in astroparticle physics and cosmology, where you have this dichotomy between big experimental collaborations and smaller theory collaborations. It's increasingly true in collider phenomenology with the release of open collider data sets. And this is something where we need to make sure as a field that what's good for the science should also be good for careers. Good for people on the theory side doing this type of work and making sure that it gets recognition, but also protecting those who are working on the experimental side to make sure that they have priority in the access to their own data first. And then the last example I'll have here is venturing into the dark sector. I already mentioned about these hidden sector portals, and the dark matter new initiatives is a really great thing that we're seeing in our field for developing like G2 prime dark matter technology. But what's amazing to me is the way that the theory community has been engaged with this, engaged in collaborating in a kind of deep way on this new generation of experiments, from conception to design to analysis to interpretation, really creative ideas like making beams of dark matter or exploring sub-GeV or even sub-eV dark matter with connections to neutrino physics, connections to quantum information, but a level of embedding where sometimes I've heard people say, oh, that person's no longer doing theory, they're doing experiment. And I don't think that's really right. This is really a synergy between people of different backgrounds. And I think it's been really exciting to see the collaborations that are developing between these two communities. Okay, how am I doing with time? I have all the time in the world, but I'll wrap up soon. Remarkably, I've been talking at a slower rate than I usually do. And so this slide is actually not as necessary as I thought it was going to be. So I have one more example. So I've told you about the ways that theory is using a diverse range of tools, using effective field theories, using machine learning, using novel concepts and technologies, using collaboration with experiment. And with apologies to Gertrude Stein, and then there's using everything. You know, that one of the things that I really like about being part of the theory community is the way that we can link together a diverse range of tools and techniques and experiments, that we have this freedom to be the glue between the different frontiers in our community. And for me, this is highlighted by an example with my collaborator, Ian Molt, who gave a beautiful talk this morning in the TF07 session. And I just want to share with you, not the details of that, but how it represents this connection between areas. And so this is a case of reaching across disciplines to define non-Gaussianities in quotes in collider energy flux. And this is a case where we're taking a technique from collider physics and QCD. In fact, a technique that Steve Ellis, who's now retired, he was in the audience, and I saw kind of tears in his eyes that his ideas were being revisited. And a technique from collider physics and QCD, interfaced through the lens of cosmology, and this word non-Gaussianity is not a word that we use in collider physics, but it's appropriate to use in a cosmological context. Then computations done through the lens of conformal field theory, and this mini lecture that you got about the operator product expansion, that's actually the way that you can do theory calculations to predict this. And then analyzed with public collider data. And so this plot here really represents a synergy between a bunch of different threads. It's connecting short distance physics to infrared physics, but mathematically they're defined by the same type of structure. It's connecting phenomenological physics to formal physics, but ultimately we're one theory community. It's connecting theory to an experiment in a way where I'm really excited for more explorations along these lines coming from the real experimentalists who can make this plot with actually appropriate error bars. But this linkage between UV and IR, this linkage between phenomenological and formal, this linkage between theory and experiment, that's what the theory frontier is all about. linking what is possible to what is. So with that, let me just leave you with my take-home messages. Theory has played, and I think will continue to play, a phenomenally important role in high-energy physics. Investments in the possible drive the science drivers. And I want to emphasize the importance of enabling technologies, enabling concepts, also the importance of developing a vibrant, inclusive community. Theory empowers experiment, experiment empowers theory. Tao Han likes to describe this as the two legs of theory and experiment moving together. And then high-energy theory is a vibrant intellectual community in its own right, and I'm really proud to be able to represent them on this stage today. Thanks very much.
All right, thank you, Jesse, for that phenomenal talk. I'm afraid I can never give a talk again after that. Do we have questions for Jesse?
So thanks, that was a really nice talk. As an experimentalist, I wanted to add, you had this nice list of how theory is really necessary for planning, analyzing, and interpreting experimental data. I think it's worth explicitly highlighting that theory is also critically important for comparing experiments across energy scales, detection techniques, detection materials, beams. We really need that, so thank you.
Great, thanks for making that connection.
Oh, yeah, thanks. Yeah, so maybe I can ask a question. So thanks for mentioning providing new like 4-pi coverage and valuing the independence. So this is a question I've asked you, and I've asked many people in the room, that what are the actual mechanisms that we can ensure that we value independence, and also people who work on new directions in the theory frontier as junior people, like in the postdoc or student level? And how can we incorporate this mechanism in the hiring process to make sure that we're not just hiring from a closed circle of people? Thanks.
Thanks, Yudai, for the question. So the short answer is that I don't know. I feel very fortunate that in my career as a theorist, I've had the opportunity to explore a wide range of phenomena. But I'm also currently a faculty member at MIT at an R1 university. And so I'm in a particular place of privilege, and I try to grant that freedom to the people in my orbit. But when it comes to coming up with an interesting idea and submitting it to comparative review, this is a challenging question. So I don't have an answer to you. And so putting that brown circle there is to highlight that it's something that we need to think about. I don't at the moment have good suggestions about how one can approach that, and I'd be curious if other people have thoughts. But I think it's something that we need to think about, and think about ways that we can make sure that we have diversity, intellectual diversity, in the types of things that we support. That said, having served on various panels that have done a kind of comparative review and the like, I think that there is, at least within the theory community, a sense of needing that balance, and a sense of needing to allow for some degree of exploration. But it may not be enough, and it's certainly something that can be stressful for early career folks who have an interesting idea but aren't established enough to feel like they could pursue it. So it's an important thing to raise. I wish I had an easy solution, and I don't.
Thanks a lot.
Okay, my comment is just adding to the first comment or question. Can you hear me?
I'll just stand over here. Yes.
Okay, my comment is adding to the first comment, basically, that it's too loud for me. That theory, yes, you like inspire experiment and stuff, and people say that physics is experimental science, but all these measurements which we do and which feed into theory gives us the understanding of the world. So I would add to what you said, that it becomes a part of just a culture of the humankind, right? That's an essential. Still working? Okay, it's just an essential pillar of the whole enterprise, is connecting what we do with everything else.
Yeah, thank you for that comment. You know, sometimes I have to remind myself that it goes in both ways. That when being trained to be a phenomenologist, I was like, okay, I have this big idea, but I need to turn it into a smaller thing that can be measured. And then sometimes I have to remind myself, oh wait, the small thing that I measured, it has bigger implications. And I think this is something that theory does a really good job of, and I think is an essential way of communicating the importance of experimental results.
We've got one in the audience, and then we'll take the one from Zoom.
So what's so wrong about human neural networks?
So what's so wrong about what?
The human neural network.
Oh, what's so wrong about the human neural network? Oh, I am so glad that you asked. I am so glad that you asked, because I think that we deserve the trophy for the LHC Olympics. Okay? And, you know, I'm all for anomaly detection algorithms, and I think it's actually a really great development for the field. But sometimes you just have to look at the data. And what we discovered, Dave, I don't know if David Shee's in the audience, so he's the person who prepared this analysis. What he did is he did something that was good. He gave a sample of what the background could look like as a training set for us. But then in the real challenge, what he did is he used a different background model. But what he did is not only use a different background model, this is unfair to David, but he randomly flipped a few switches in Pythia. And that random flipping of a few switches in Pythia generated a very weird kinematic configuration that, if you combine that with generator cuts, actually generated a feature precisely where we found it. So we found a gigantic bump in a 3-jet configuration that was caused by not actually treating the Monte Carlo correctly. And so we identified it. And then you can say, why did the neural network not find it? Why did we find it and the neural network not find it? The neural network didn't find it because there was a prior that the anomaly was going to show up in 2-jet configurations. Our human neural network says, oh, let's see, maybe they're going to actually do some more complicated thing. We're actually building some kind of cascade decay new physics model. And we said, let's just check 3-jet configurations. We saw this gigantic feature. Now, I think if you'd actually loosened the prior on the neural network and said, hey, neural network, don't just look in 2-jet, but also 2-jet, 3-jet, 4-jet, everyone else would have found the same thing that we found. But this is a case where it was a combination of needing to have this powerful, neural network structure, but also domain knowledge about where anomalies could show up. And I was really surprised. I was thinking, geez, what is this challenge where I thought I was doing machine learning, and instead of going back to like my grad school days and doing like model building and trying to talk about, multi-jet resonances. And I think that is also an important skill. So we can't just leave everything to the machines. The domain knowledge that we've accumulated as a field is also essential. And especially in cases like anomaly detection, where we have the chance of maybe not finding or finding new physics, depending on the priors that we have.
So Mariana, if you want to ask a question.
So thank you for a great talk. I come from the quantum sensor theory, and you have mentioned that there is a increased collaboration of theory and experiment, but there is also increased collaboration of completely different fields. Like, for example, with some of the quantum sensor experiments, you need to understand the particle theory part, the atomic or molecular theory part, the maybe nuclear physics part, and as well as understand experimental capability, what can and cannot be done, say, in the next 10 years. So how do we actually encourage the collaboration of different fields, and how do we make sure we all actually talk the same language to really maximize the wondrous opportunity that came up in the past 5-10 years?
Right. So first, thanks for pointing that out. It was really cool for me to learn from one of my former students that techniques that I would call part-time distribution functions turned out to be relevant for understanding the electron response of condensed matter materials relevant for dark matter detection. And the fact that people are also talking about needing to put certain type of quantum sensors underground to shield from nuclear effects, like that's like really cool crosstalk. And then you're asking the question, how do we make sure that those things are encouraged? We are the community. We can encourage that. And that can be one of the messages that comes out of this process.
Great, thanks. Looks like we got one more question, and this might be our last for time.
So
expanding off of that question, off of what went on in the answer to the question, how did the humans get it wrong? Well, then you mentioned your idea that it's because of all these models, they have a certain prior, and that prior should be loosened. Well, have you tried integrating that prior into your own method to test that?
Right. So, so the question is basically, can you incorporate the knowledge that we already have as theorists into these type of anomaly detection algorithms? And the answer is, I personally haven't been trying to go in that direction yet, but absolutely that's where this field is going to go. And this is emphasized in the machine learning talks early this week, that machine learning is just a tool. We get to choose how to turn that tool into a paradigm. And we don't have to give up on things like proper error quantification, like that kind of matters. Understanding what the priors are, not just letting those priors be implicit. Incorporating domain knowledge, and that's a thing that we definitely have to do, and we have to do our own R&D in our own world to figure out how to apply these amazing machine learning techniques, but apply them in a way that's appropriate for high energy physics discovery applications. And so this is an area where, that's why I put it on the slide, of a thing that I think is going to grow continuously over the next decade.
Great. I think for time, that'll be it for now. So let's all thank Jesse again.